Welcome to the sixth part of the Introduction to Haskell course, and in this part we're going to be looking at recursion and folds in Haskell. We'll start off with recursion, and to introduce recursion I'm going to first talk a little bit about looping, which is the concept of repeating the same action multiple times. This is most common in imperative languages, but in general the concept is very common in programming in general. So actually in the first video of this course, when we were comparing some imperative syntax to Haskell syntax, we saw an example of a loop in the imperative program. The thing is, with Haskell, we don't have a syntax for loops. So there are no for loops or while loops or any kind of loops in Haskell. The basic mechanism for looping in Haskell is just recursion. So what is recursion exactly? We could define it as a process of defining a problem or the solution to a problem in terms of itself or a simpler version of itself. So with recursion, what we are doing when we're solving a problem, we're defining functions in a way that we are breaking them down to solve smaller versions of the problem on each step, which is sort of like looping. This definition might be a bit confusing right now, but once we get into the example, it will make more sense. In any case, recursive functions are those defined in terms of themselves, right? So as the definition says, this means in practice that the function body includes a call to the function itself, right? So we have a function, for example, call it f1, and in the body of the function f1, there is a call to the function f1, to the same function. Okay, so if a function is calling itself, then right away we have a potential of infinite loops, right? It can just call itself indefinitely. So that's why when we define recursive functions, we must have some base case. The base case is when it is matched, it stops the recursive calling and actually returns some value. So this stops recursion and gets us a way of infinite loop or infinite recursion, might be better to say. And the recursive case is sort of the case that is breaking down the problem into smaller ones. And those are patterns that continue recursively, and in the recursive cases there is always a recursive call to the function itself. So let's take a look at an example of a recursive function, and this function is used to calculate the sum of all natural numbers up to n, and including n in this example. So we can define it as name it sum n, and it's a function that accepts an integer as a natural number and returns the sum of integers, so the result will be an integer as well. And then here we have the two cases, the base case and the recursive case mentioned in the previous slide. And the base case for us in this function will be if the argument is 0. So that's a very simple case, because we know that the sum of all natural numbers up to 0 is always going to be 0. This is our base case. For any other number, and if we are talking about natural numbers, that will be any number greater than 0. So x will match any number greater than 0 here. We can define what the sum of all natural numbers up to that number is by saying it's that number plus the sum of all natural numbers of that number minus 1, right? So that's the recursive thinking of breaking down the problem into small steps. Okay, so it's this number plus whatever is the sum of the previous one. We take out one part of the problem and let recursion solve the rest. Okay, so this might be a bit tricky to envision in your mind how it gets executed, but if we break it down here below, it might help. So let's say we look at sum n of 4. So we say, okay, sum n of 4 is 4 plus whatever sum n of 3 is. Okay, then sum n of 3 gets applied, and we still have 4 from the previous call. Then we say, okay, sum n of 3 is 3 plus whatever sum n of 2 is, and so on, until we finally get to 0, right? So if we get sum n of 1 is 1 plus sum n of 0, and we know that this is our base case. Sum n of 0 will simply return 0 and recursion stops, and we have defined our sum n of 4 as the sum of all these numbers with recursion, and the answer is 10. Recursion is very often used with lists and is very useful in that case. And actually the map function we talked about before is actually defined using recursion in the prelude of Haskell. So we defined it with list comprehensions to use an example for list comprehension, but now we can actually use it as an example for recursion as well. So with the map function, we have our base case here, which is most importantly the empty list. Okay, so if we get an empty list, we don't really care what the function is because there's nothing to apply it to. And the only thing we can do is just return an empty list. That's our simple base case. And then any other case, so as we know, this pattern XS will be the head and the tail of the list. And if it's not an empty list, then this pattern will match at least one element in the list. And in this recursive case, then we want to apply our function f to the head of the list and concatenate with the rest of the list, but with the rest of the list in a way that we are still applying f to each element of the rest of the list, right? So this is the recursive call of map with the same function and the tail of the list. When it comes to defining recursive functions, I found the 4 steps given by Hutton's book Programming in Haskell very useful and helpful, and I think this is a good book for learning about Haskell. If you're interested, you can check it out. The 4 steps are as follows. Number 1, we define the function type. So we define the function type signature, and this helps us because we have to start thinking about the types of the function itself. We know what we are going to take in as arguments. We know what we want the result to be. So it's a very good first step when starting to think about how we're going to define the function. And in general, it's considered good practice to write function type signatures always. The second step is then to just enumerate the different cases that we expect. So usually we can differentiate between the base case or the simple cases and the more complicated cases. So for example, with lists, usually we can consider the case of if we get an empty list versus a non-empty list, and we can enumerate those cases, not defining them, just listing what they might be. With the integer type of function, like the sum of natural numbers, our cases would be if the number is 0 or if it's any other number greater than 0. So number 3, we take care of the simple cases first, which are usually the base cases. They are much easier to define, right? So like we saw, sum n of 0 is simply 0. Also in map, if we get an empty list, we simply return the empty list. We don't even have to worry about applying the function to anything. And then the final step is to define the other cases. And in that step, we need to think about how do we actually break down the problem? How do we calculate the wanted result using the recursive call and potentially any other functions that we might need in this recursive cases. Usually the 4th step is for recursive cases only. So let's take a look at the 4 steps in practice through an example. Imagine that we need to define a function that takes in two integers and raises the first integer x to the power of y. The first step is to define the function signature for our function. Okay, so we know it will take two integers, and raising x to the power of y, if they're both integers, will also return an integer. The second step is to simply enumerate all the cases. So we start with the simple ones where each of the arguments is 0. So the first case, we have a power, so the y is 0, which means raise any number to the power of 0. That will be our one simple case, right? Then the second one is if we get a 0 as the number raised to the power of anything else. We also know this will be a simple case. And then finally, we have power x and y where neither of those is 0, and that's our a bit more complicated case, the recursive case. And those are the three cases we expect, so we simply list them out in the second step of defining our recursive function. The third step then is to take care of the easy cases, which those being our two cases. And we'll say that power of any number, so any number to the power of 0 will always be 1. And the second simple case is 0 to the power of anything is 0. I'm not actually sure, like in mathematics, maybe there is some debate, maybe 0 to the power of, what is 0 to the power of 0? It's still 0. In any case, for this example, we will say 0 to the power of anything is 0, and anything on the power of 0 is 1. And then finally, the fourth step is to define the final recursive case, the tougher case. And there we have power x and y. So we can say, in general, if we raise number to a power, it means we are just multiplying it by itself, whatever number of times is defined in the power argument, so y. So we can just take x and break it down. So x to the power of anything is x to the power x times whatever the power of x to y minus 1 is. Okay, so if we have 2 to the power of 5, we can say 2 to the power of 5 is equal to 2 times 2 to the power of 4, and so on. So we are breaking it down in the recursive case. So we are decreasing y by 1 on each recursive call, and eventually y will reach 0, and in that case we will return 1 or times 1. So, and the recursion will end. One more example here with lists instead of integers here, and we want to define a function that returns a new list with only the even indexed elements. And I put a star here because in this example I'm going to consider the 0 index of a list, the first element, as an odd index, right? So in other words, we want to return every other element. So the first one we don't want, the second one we want, the third one we don't want, the fourth one we want, and so on. Okay, so we define the type signature as the first step. We call this function evens, and we take a list of whichever type, type A, and we return the list of the same type. It's simply the same type of elements, just some are filtered out. We, in the second step, enumerate our cases that we expect. So we, first of all, can expect the case of empty list. Okay, we can expect a case with just one element in the list. We expect this because if there is one element in the list, then we know we don't want it. Any other case will mean that the list has at least 2 elements, 2 or more. Okay, so this pattern matches. Now, I think we haven't seen this pattern before, but it's nothing more than this is the head of the list, the first element of the list. X in this case is the second element of the list, and XS is the tail of the list. So we can pattern match on lists with multiple elements, and we can always use XS as the rest of the list. But the thing is, we can only go from the front, right? From the first element, second element, and then the rest of the list in this case. Sometimes you might want to match from the back of the list. So maybe you want to get the last element, the second to last element, and so on. But you cannot do this with this sort of pattern. So using the cons constructor, we know that it appends elements to the front of the list, to the beginning of the list. So we can only use it for the beginning of the list. If you need the last elements, you need to come up with other ways to do it. In any case, our third case that we expect is a list of 2 or more elements, which will be also our recursive case. So the step 3, we take care of the simple cases, which is the empty list. If we have an empty list, there are no even indexed elements, and return the empty list. If the list has only one element, as I said, we will consider this an odd indexed element, and we will also return the empty list. So we will skip that first element of a list. And then the recursive case, in the fourth step, we have our 2 elements and the tail of the list. We want to, that's why I use the wildcard here, because we don't care about the first element. We will discard it, right? We want the second element that we consider even indexed. So we take the second element, X, and we join it with the recursively processed tail of the list, XS. So we say even the even indexed elements of this list of 2 or more elements are its second element and whatever the recursive process of solving the rest of the list brings us. Now we get into folds, and folds might be a bit difficult to understand, and in general we are entering the part of the course where things get a bit more difficult. But in any case, keep going. So folds are a higher order function, HOF abbreviation here, higher order function that process a data structure. We will be using mainly lists for an example, but they can be defined to work with any other data structure, I think. And they build some return value. So in other words, they sort of flatten a data structure to build a return value. They will take in 3 arguments. Number one is the function that combines the elements of the data structure. Okay, so that's our combining function, argument number 1. 2 is the starting value. So because we are building a return value, we also need to give it a starting value to build the final return value from. And 3 is the data structure where the elements are stored and from which we build our return value. So there are 2 basic folding functions in the prelude, and their basic versions are foldr and foldl. Foldr stands for fold right, and it means that the combining function is applied in a way that it associates to the right, while in foldl the association is done to the left, and we'll see what that means in examples next. Let's start with fold right. So it says here that the rightmost elements are evaluated first in fold right. And strictly speaking, this is true. So if we have strict evaluation, then with fold right, the rightmost element of the data structure, or let's say list, will be evaluated first. However, Haskell is a lazy language, so in some cases, the rightmost elements won't even need to be evaluated because the result of the entire fold can be known, but those are some special cases. In general, the most nested brackets will be on the right, and the rightmost elements will be evaluated first. So foldr, the definition of this function, it can be defined as such. So our type signature is a function that takes in arguments of type A and B and gives back the result B. This is our combining function. B is our second argument to the function, type B, and it is our starting value. And then the list of A's is a data structure that we want to fold over. And the final result is a type of B. So the final result will match the result of the combining function, and the starting value B must match also the second argument of the combining function. Okay, so we have two general cases with foldr. It's also defined here with recursion. The base case if we get a function and a value, but we get an empty list. In that case, we just return the value because we don't have any elements in the list to apply the function to. And the other case is when the list has at least one element. We apply foldr such that we apply the combining function to the head of the list and know that the combining function takes in two arguments, right? So we give it one argument, the A, from the head of the list, as the list is of type A, so we give it the first argument A, and then the recursively processed tail of the list with the same value, the same starting value, and the same function. Okay, so the recursively processed tail of the list will be the second argument to this f of x. Okay, so what I was saying with laziness, sometimes f applied to x depending on the function and what we're working with. For example, with booleans, it's easy to imagine that we can know the result of the entire fold just by applying f to x, and we can disregard the entire recursive tail because, for example, if the function is logical AND, then we know that if x is false, the whole thing will be false, right? So we can, Haskell will use laziness in that case to completely disregard and say, I don't need this rest, I don't need to evaluate the right part of this. I know that the whole expression will be false because x is false. And the logical AND, with logical AND function, we have to have all booleans as true to finally evaluate to true. Everything else is false. Now, an example will help illustrate how the association to the right of fold right actually works. So imagine that we have a summing function and we want to define it with foldr. So we take a list of some numeric elements and we flatten it, right? We give back just a return value that is the sum of all the elements inside the list. So we would define this as foldr. Our combining function is the plus operator. Our starting value will be 0, and the data structure we want to apply it to is our list that we give to the sum function. How would this be actually executed then? So we have imagined that we apply it to this list of 1, 2, 3. From the definition of foldr, we know that we would be applying plus. Okay, so here I used it as an infix operator, which we can do with plus and minus and so on. But in reality, plus is here applied to the head of the list first. So plus 1 and the recursively processed tail on the right side. Okay, so foldr plus again the starting value 0 and the rest of the list 2 and 3. So then we get again plus applied to 2 and the recursively processed. Then we get 3 applied to plus applied to 3 and the recursively processed rest of the list. And then finally we get to the case where we have an empty list, and in which case we just return the starting value, which is 0. So this evaluates to just 0. And what we end up with is the most nested brackets are on the right. So we would first evaluate 3 plus 0, then 2 plus the result of 3 plus 0, and then 1 plus the result of 2 plus 3 plus 0. We finally get to 6. Okay, so in this case, this is a summing function. So with a summing function, we know we have to go through the entire list no matter what. We have to sum up every element, right? There is no way to use laziness to stop the execution sooner, know the result sooner than go through each element in turn. Okay, so in this case, laziness is simply impossible. We have to add up each element. So what I was saying about foldr sometimes being able to make use of laziness, it does not apply to summing functions. Let's take a look at another example, and I'll try to illustrate something else with this one. So imagine instead of a summing function, we have a product function. Again, for a product function, so we want to multiply each element in the list. Again, we have to go through each element, so no way of taking advantage of laziness to get the result sooner. We have to know each element. And in this case, we can define it as foldr, and then our combining function is multiplication. Then our starting value must be 1, because we just want to multiply by 1 at the end to keep the result. If we multiply by 0, we will get, everything will be 0. Okay, so we can actually think of foldr or folding in general as a replacement for the cons operator with lists, right? And we replace the cons operator with a combining function. So if we have a list of 1, 2, 3, then if we rewrite it in a way using cons, then it's 1, cons 2, cons 3, cons the empty list, right? But if we use foldr, then we can actually read it as 1 plus 2 plus 3 plus 0 instead of empty list, right? So you can see that this is very, very similar, and it might help you think about folding this way as replacing the cons operator to flatten the list into a value. Now let's take a look at fold left, foldl. With foldl, the leftmost elements are evaluated first. The functions associate to the left, and so our foldl function definition and type signature will be a bit different than foldr. First, we have the combining function again, takes in 2 arguments, a and b, and gives back a type of a. We get the starting value, which is of type a, and we get our data structure, our list of b's, and finally the result of the function is a. So a as in the final result of the combining function, and we can see that a here, the type of a is the first argument to the combining function, so it matches our starting value a, and the second argument matches our element type of the list, so b. Now let's look at the cases that we have defined here. So the base case is the one when we get an empty list, and same as foldr, we just return the starting value that was passed in. The foldl in the case of a list of at least one element is the recursive case, and here we have a slightly different definition from foldr, where we apply recursively foldl with the combining function again, right? And we basically recalculate the starting value that we will be passing to this recursive call, right? And we calculate it by applying f to our current starting value and x, the head of the list. So we can see here we applied the combining function to 2 arguments, which is enough to complete the function and get back a result of type A, which then feeds again the f of the recursive call. With foldr, we had just f of x and then applied to the recursively processed tail. So we only applied f to 1 argument and the recursively processed tail. Instead, here we apply f to 2 arguments, so we can get a value from this expression right away. So this is like a bonus for, or a plus for foldl, that we can get a value from this expression, and unlike in foldr, we cannot get value from the function application, because we say we apply it to 1 argument, so that's currying, and then the second argument will be the recursively processed tail. But what is the second argument, right? It's recursively processed tail. Okay, so to get the result of that, you again need to recursively process. So you need to go all the way to the right side to finally get a result that you can use, and you can build an expression that is that uses up a lot of memory that way. While here, since we can get some value that will be small in memory, we basically foldl is a bit more memory efficient, but it has some other drawbacks as well. In any case, the second argument or the third argument to this foldl function is then the rest of the list. Let's see how that actually gets applied in the same example of a summing function where that we tried with foldr as well. So we have the combining function plus, we have our starting value 0 and a list of 1, 2, 3. So on the first iteration, when we apply fv and the list of 1, 2, 3, we will get back foldl again, right? Foldl recursively called on the function f, so that's our plus, and then the result of fvx, and in this case we can write 0, which is v is 0 starting value. So it's basically plus applied to 0 and the head of the list 1, okay, and that's in brackets, and then the rest of the list is fed to this recursive call of foldl. On the next step, again, so our starting value is now 0 plus 1 in brackets, and on the next iteration, again, we call recursively foldl with the combining function plus, and in this case we apply 0 plus 1 and we add the plus 2. So what we got for the starting value in the second iteration is not 0 but 0 plus 1. So we apply f to 0 plus 1 plus x, the start of the list, which is in this case 2, and the rest of the list. We do the same for the final element 3. We get back 3, and then we finally have the case where we are left with an empty list, and with an empty list, in that case, this application fold plus this is just this expression, right? Just the v. And so finally we just evaluate this expression and we get back 6. But the important thing is that we see that from the application, the most nested brackets are on the left, or in other words, the combining function associates to the left with foldl. To bring back this intro to fold to an end, I just want to make a note on the placement of the starting value v in the combining function. So with foldr, the first argument of the combining function is an element from the list, while in the foldl, the first argument is the accumulator value. Okay, so let's say we want to define a function that returns the length of the list with foldr and foldleft. So I'll call this length r. And how we can do it is if we use foldr and then we give it the combining function. And our combining function is with foldr, the list element is first. And for this function, we just want to ignore the list element. We don't care what it is. We know that if it is there, we just want to increase our count by 1 because any element adds to the length of the list, right? So then we just say n plus 1. That's how we will combine things. And our starting value is 0. Of course, this is using ETA reduction. So like length r xs here could be written as well. And length of r 1, 2, 3 is 3. Okay. The difference with using foldl for the same thing is that in our lambda function as the combining function, n, our accumulator or the starting value, comes first in the combining function, right? And the list elements that we ignore again is second. We have the same logic like n plus 1, right? We are just counting the number of elements to get the length of the list, and starting value is 0 the same way. Both work the same, but you can see that n has a different position in foldr and foldl. So keep that in mind. That's the end of this presentation. We covered an introduction to recursion and an introduction to folds. And now we will go into the practical part to see these concepts in practice. We'll get started with exploring recursion and folding on some examples. So I prepared here a list of 3 functions that we will define using recursion, foldl, and foldr. So we'll start with a simple function sum, which needs to take a list and a list of numbers and give back the sum of all its elements. Okay, so I'm going to call this function sumr for recursion. And the first step with defining recursive functions is, or in general to defining functions, is to write the type signature. So I know I'm going to get a list of numbers. So I'm going to use the class constraint num a, and I'm going to get a list of a's, and I'm going to give back a type a, which will represent the sum. So the next step for recursive functions is to think about all the cases that we could get. So obviously the base case or the most simple case here is going to be an empty list, right? And the other case is going to be a list which has at least one element. And we can enumerate these cases this way. And now we go to the simplest case. So we just need to answer the question, what is the sum of an empty list? That's pretty simple. We can just say it's 0. And then the other case, the recursive one, we need to think about how to define sum for this case. So we take x as the head of the list, and we say the sum of this list is this head of the list plus whatever the sum of the rest of the list is. Okay, so my IDE is complaining, but it's just suggesting to use foldr, and actually this is a valid syntax, and we can load it in GHCI. So load session 6, and we can say sum r of, let's say, 1, 2, 3, and we get back 6, which is correct. So that's how we would define a summing function using recursion. Now let's try to define the same function with the folding function foldr. I'm going to call this sum fr, standing for fold right. And again, we can write the type signature, which will be same, right? We'll still get a list of numbers. We'll still give back the sum, which is just a number. And with folds, so we want to write a foldr function that so foldr function takes in a combining function. If we are talking about the sum, then for us this combining function will be simply the plus operator, and we need to give it a starting value, which is 0. And this is okay using ETA reduction, but if we want to, we can put the list argument here, and then the final argument to the foldr function is the list that we want to fold over. The IDE is saying use ETA reduce, okay, to remove the excess on both sides, and also to use sum, of course, because sum is a predefined function for this. But this is not the point of this exercise. We just wanted to see how foldr works. And while we're at it, we can just copy this over to define it with foldl. So oh, I forgot the f here. So some fr and some fr, some fl here for fold left. So here we will use foldl, but the order of the argument is still the same. The application is a bit different, as we saw in the presentation. For our summing function, it doesn't matter. So basically, foldl here can have the same definition as with foldr. So the combining function is plus, starting value is 0, and we apply it to the argument xs. And this is both fine. So we can reload this module and then say instead of some r, we can use some fr, we still get 6, some fl, still get 6. Okay, so those are summing functions defined with foldl and foldr. Now let's move to the second function we want to define, which is concatenate. So this will be a function that takes two lists and joins them together. So we know we have the function plus plus for this, but the point of this exercise now is to define it using recursion in this case, and then later with folds. So we'll call this concatenate r, and the type signature will be two arguments, both lists of type A, and finally the result is again a type of list of A's, right? The same type, just joined together. Concatenate R. So now we think about the different cases we might encounter. So we have two arguments. Our general cases are if the first argument is an empty list and we get ys, that will be something. Then concatenate R with the first list being something and the second list being empty. We can think of that case. And finally, we can think of a case where both lists are not empty. Okay, so let's take care of the first examples first, which are simpler, right? Because if the first list is empty, then the concatenation of those two lists is simply the second list. And the same goes for the other case. If the second list is empty, all we can return really is the first list. And that leaves us the more complicated case, the recursive case that we need to define. So we want to join them together. And of course, what we could do here is xs plus ys, right? But this is not a recursive definition. We need to recursively call concatenate r, and we don't want to do this. But instead, what we can do is replace this xs with a pattern match of xs. So x is our head of the list, and then we can concatenate that head of the list to the result of concatenate r xs, the tail of that same list, and ys, right? So we take the first element, and we concatenate it with the rest. So in the recursive call, we will again take the second element and concatenate it until finally we exhaust the first list for it to be an empty list, and then just concatenate with ys, and that will be the end of execution. So we can check this in GHCI, concatenate R, and if we have two lists, say 1, 2, and 3, 4, the result is 1, 2, 3, 4. So that's concatenation using recursion. Now let's define concatenate with fold. So we'll use foldr first. We'll define this as concatenate fr. The type signature is again the same, two lists. Give back one list of the same type. So concatenate fr, in this case we want to use foldr. So our combining function will be just the cons operator here, right? So we'll be taking elements from a list and concatenate them to some starting value, and our starting value can simply be one of our lists. Instead of starting from an empty list, right, we can just say the starting value will be xs, and then we'll concatenate it to ys. Now the thing with this is, if we load it and try to concatenate fr and 1, 2, 3, 4, we'll get back the reversed order. Well, not the reversed order, but 3, 4, 1, 2. Okay, so in this case, the way we wrote it, the first list 1, 2 is the starting value, and because of the way arguments are applied in foldr, that starting value ends up at the end, like we saw in the example in the presentational part. The 0 of the summing function was at the end, at the right side. So the same thing happens here. The xs will be at the end, at the most right side with the cons operator. So 1, 2 will end up at the end of the list. So we can fix this by reversing these two arguments, right? So our starting value will be, in this case, 3, 4, and that will be far to the right. And then 1 and 2 will be joined with that. So if we reload and try this again, then we get the correct order. So maybe it might be a bit confusing, but it's useful to write out how this is actually applied. So I'm going to do that here, actually prepare it here. So we have foldr using the cons operator. Our ys, in this case 3, 4, the second argument, is our starting value, and 1 and 2. So we know that foldr will take one element from the last argument, the data structure, and in this case this is 1. Then it will apply the combining function, or basically it will combine, this is the same as writing the cons as a function, and then 1, and then foldr, so on, right? I just wrote it here this way because it's easier to read. So 1 cons, and then the result of foldr again to the same thing, 3, 4 preserved here, and then just one element from the list popped, and we're left just with 2. Then again it will take as the other element, again the head of the list that remains, and apply cons to the result of here. And now we get the case where we have an empty list, so the folding stops, and the final result is 1, 2, 3, 4. So that's how we get to our result with foldr. Now let's do it with foldl. And in general, we kind of want to do the same thing, right? We want to, so with our sum function, it was like exactly the same. We just changed foldr to foldl. and here we would like to do the same. So foldr, we replace it with foldl, but we get an error. So something's wrong with the types, and this is because of the way foldl applies its arguments, right? So we take a combining function and we can check the type of the cons operator. It takes an element and a list and appends that element to the head of the list, right? So the first argument must be an element and the second argument must be a list. So in foldr, our first argument to the combining function is an element from the list xs. But in foldl, the first argument is the accumulator value and then the element of the list. So as it is, that means that the cons operator would be applied as in accumulator and then x, right? Or in other words, accumulator x. But our accumulator here is a list. So we would be applying a type of a to a list of a's to a, right? So this, of course, doesn't work. What we want to do is reverse that order, right? We want to apply x first to the cons. So instead of the cons, we could write a lambda function that says, okay, we accept an accumulator and x, and we return x with the accumulator. And this is fine, except that my IDE is telling why not use flip, okay? Because if you notice, what we are doing here in this lambda function is take two arguments and apply a function to them, but replace the order of the arguments, right? Flip them around. And so there is a Haskell function for this that we can use, and it's called flip, and it will simply flip the arguments in which the flip the order of arguments to apply to the function, right? So this is exactly what we need here, right? Instead of accumulator cons x, we need x cons accumulator. So flip does that for us. And now we see we don't get errors. So we can reload this and try to concatenate with FL. And we still get something. So our 3, 4, the accumulator is still at the end, that's fine. But 2 and 1 are in reversed order, right? So what we actually want to do to fix this, we can reverse this XS list. So we can apply foldl to the combining function to ys, and then the final argument is reverse of the list XS. Now, if we load this, then this works fine. And I also prepared the application steps that might be helpful. So why this works this way, right? So 3, 4 is our accumulator, 1, 2 is our XS, and here it is not reversed, right? So let's check how foldl would apply this function of flip. So with foldl, the first argument is the accumulator value, right? But this is flip cons. So we flip the arguments, and then the first argument is actually the element from the list again. And this is the element 1, and then cons 3, 4, and then we get 2, and then we get 2 applied to this result, which is 1, 3, 4, right? So we can see that finally the result that we get is 2 cons 1, cons 3, cons 4. So the list that we get in the end is 2, 1, 3, 4. So that's why we need to reverse the XS list in this case for foldl to work properly. Now let's do the third function, which is concat, which takes a list of lists and concatenates them together. So we'll write this as concat r. Our type signature will be so a list of lists of A to finally give back their concatenation. In other words, just one list. So concat r, this is the recursive function. So we think of the cases first. We can get an empty list, so a list of 0 lists. That will be one case. We can think of another case where we get exactly one element. I'm going to write XS here because in this case the element of this outer list is another list, so I'm going to represent it with XS. That's going to be our other case, and then we can have the most general case, which is again a list of more than one element. And since this is a list of lists, I'm going to represent them as XSS. I think this is standard, so standard is to write S at the end. So we could still write XS, and this would still be X is the head of this list, which is also a list, so X would be a list here, and XS would be the tail of the list, list of lists. But since we know the first element is actually a list, I'm going to address it as XS. And these are our general cases. So concat of an empty list is simply an empty list, right? That's pretty simple. Concat of XS is the list XS. If it has only one list, then we just return that one list without the brackets, of course. And the recursive case is can be defined simply as, so XS, the first list, and we can use ++ here to concatenate this with the rest of concat R of the XSS. So this is our recursive case. And if we really think about it, in this case, we don't need this case of just one element, right? Because even so, if we remove this, then just one element would be covered in this pattern, right? XS would be the single element and XSS would just be an empty list. And then we would call XS plus and concat R on an empty list, which would match this pattern. So that would work too, but we can leave it in. Anyway, here the IDE is saying to use foldr, which we'll do in a second, but okay, this is using recursion. So if we reload here, concat R of a list of lists, so 1, 2, and another list of 3, 4, and their concatenation 1, 2, 3, 4. Okay, that's recursion. Now let's do the folding way. So concat here, so first foldr, so we'll call this concat fr. The type signature, again, a list of lists, gives back one list. Concat fr, we want to use foldr in this case. So we think of our combining function. So we get XSS here as a list of lists. And so foldr, our combining function is basically a list concatenation, right? We want to concatenate multiple lists that we have here together. So we can use foldr++, and then we need to think about our starting value. In this case, we want to start from just an empty list, right? And concatenate every list that's in XSS. Of course, we can do ETA reduce here to remove XSS on both sides. And probably, yeah, use concat, which is a predefined function. But okay, this is how we would define concat with foldr. If we reload it, concat fr, again 1, 2, 3, 4, and we get back 1, 2, 3, 4. Okay, now I'm gonna copy this over to the fold left implementation, and I'm just gonna rename it to fl, concat fl, and I want to use foldl. And now the question is here, can we use this the same way as we do with foldr as with sum, or do we need to change it, right? And the answer is, well, let's see what the answer is. Fl, if I just if I just replace this with FL, okay, we get back the same result. So we don't need to replace it. And why, you can figure out why if you try to work through the steps of the application of foldl with the ++ operator, and you will see that in the end you do get to this result of 1, 2, 3, 4 concatenation. Now let's get into the katas for this session. I selected 5 of them, and we'll start with this one called Thinkful. So we have a 2-dimensional list in the following format. So a list of lists of 2 elements and 2 numbers. So each list contains 2 items. Each item is an integer. Write a function process data that processes the sublist like so. 2 and 5. 2 minus 5 is -3. 3 and 4. 3 minus 4 is -1. Okay, so the first element minus the second element, and then returns the product of all processed sublists. Okay, for input, you can trust that neither the main list nor the sublists will be empty. Okay, so first we want to process the first list in a certain way by subtracting the elements one from another, and then we want to calculate the product. So a product we can calculate with, for example, a folding function. There is a predefined function called product, but let's just use foldr here because we are practicing it. So foldr, the combining function we want to use is multiplication times, and we want to start from 1 because multiplication at the end we need to say times 1 to keep the result, and we want to apply it to a list, basically a process lists. So we'll call this process data, like proc data. And so here we will define this proc data, and we can define this as, so we can map over our list, right? So we map over each element and create a new list that calculates values based on those elements. Okay, so we can use map. The function we want to map over this list, we can define it as a lambda function that so this function must take the elements of the list. So in this case we know that those elements are going to be represented as a sublist, right, of 2 elements, x and y. So this function takes in one element, a list element, and has which has the elements x and y, and we want to subtract them. So we want to subtract x minus y. Okay, that's our result. And so which list do we want to apply this mapping function on? We want to apply it to the data. That's the argument to our function. Yeah. So this is, I think, complete. Katas. We load Thinkful. Okay, and we have process data. So we can check this example. We get back 3. Okay, and this is the correct result. So the first sublist process will give -3, then times -1, and then times 1, and that will give us 3. Okay, so that's the first kata, Thinkful. Next, let's go to this one, make uppercase. It's another easy one. It's just write a function which converts the input string to uppercase. Okay, so in Haskell we know that a string is a list of characters. So I think this is a good function to write with recursion. And so if we think about our cases, the first case will be an empty list, in which case we return an empty list, right? Make uppercase of empty list is just an empty list. And then make uppercase of the general pattern of a list of at least one element, will be, so we want to turn each element of the list to uppercase. So we can use the function toUpper from the data.char module. So the function is toUpper, and we can apply toUpper to the head of the list x and concatenate it, or use the cons constructor with the recursively processed tail, right? So just make uppercase apply to the tail xs. Now ID is saying use a map. Yes, we could use map, so we could just map the toUpper function to xs. Here we use recursion. It's fine as well. We load this one from Katas, make uppercase. Let's say we have a string of ABCD, and we get back the uppercase version of ABCD. The next one will be multiples of 3 and 5. In this kata, if we list all the natural numbers below 10 that are multiples of 3 and 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Okay, so we need to finish the solution so that it returns the sum of all the multiples of 3 and 5 below the number passed in. Additionally, if the number is negative, return 0. Okay. If the number is a multiple of both 3 and 5, only count it once. Okay, so don't count it twice. Okay, so obviously we're gonna need to sum up something. So we can use foldr, and we will get an integer. We need to create a list of numbers from 1 to that number minus 1, because it says below that number passed in. So a list of numbers which are multiples of either 3 or 5, and then sum them up, right? So we can write something like foldr, we will use plus, starting value will be 0, and then we want to apply it to this list of, I'll call it multiples, and we will define multiples using list comprehension. I think it's quite nice in this case. Of course, here we can use sum instead of foldr plus 0, but since this session is about folds, we'll keep it as foldr. So multiples will be, remember the syntax for list comprehension is, so the generator, we just want the number x, and then x is taken from some list. So the list we are going to take it from is a list from, we could say 1 to number minus 1, right? Number being the number passed in. But since we know 1, 2, they are not multiples of either 3 and 5, we can start with 3 instead. And okay, that's it. So now we want to make the guards for this, right? We want to only take x if x modulo 3 is equal to 0. So if it's a multiple of 0, but we also want it if, so we can say if, we can use the or clause, double vertical line. So we can say x mod 3 is equal to 0, or x mod 5 is equal to 0. And so this is still one guard. Oh, I guess we don't even need to use or, we can just write it as a multiple guards, right? No, because with multiple guards, then each of them has to be satisfied. So multiple guards would be the same as writing and, right? But we don't want and here, we want or. And that should be it, right? We create the list of all multiples and we sum them up above. If we load Katas multiples of 3 and 5, and we have solution, so let's say here we get 10. So below 10 are 3, 5, and 6, and 9, and the result is 23, and we get 23. Okay, those are the multiples done. Next one, let's do break camel case. This kata requires us to complete the solution so that the function will break up camel casing using a space between words. Okay, so camel casing is where words are not separated by a space, but instead the pattern is like lowercase and then uppercase letter to separate the words. So in this case, camel casing written in camel case, we need to separate it in our function with a space, but we keep the case as it is. Okay, identifier all lowercase, so nothing to split. Empty string is still an empty string. Okay, so I think this is a good problem to work out with recursion. So we accept a string, we can think of our base cases as an empty list, and if we get an empty list, we return an empty list, right? That's pretty simple. If we get a list of one element, right, then we can't really have camel casing, and we return the same list of one element, right, or of one character. Okay, and then finally we have our general case of xs, and so what we want to do is check. So we can use the functions from, again, import from data.char, and there are functions called isLower and isUpper, which check if a character is lower or is upper and returns a boolean. And then we can write an if statement. So if our x, the first character, is lower, so if lower x and is upper applied to the head of xs, right? So so if x is followed by an uppercase, if x is lowercase and is followed by an uppercase letter, then we have camel case and we want to separate them, right? So we're going to separate them as so we can say return x plus space in between, and yeah, so just insert the space in this place and return and concatenate it with the recursively process, so solution of xs. Else, if it is not space, then we just concatenate x to the recursively processed tail without sorry, so I use double quotes here. I need to use single quotes, so we want to use the char. Couldn't make XP type is upper. I'm not sure what's wrong here. Is something with my function operator? Why? Okay, so this is fine. Okay, I guess we can do compose head and is upper and apply to xs. No. Probably because of the end. Yeah. Okay. Sometimes Haskell syntax is a bit like this, and it's not clear what gets applied to what. But okay, so we need to separate the expressions for the AND operator. Okay, so this looks good. We'll load it, Katas break camel case, solution of camel casing. Is camel casing. Okay, so that works. So if we have just camel, it's just camel. Okay, if we have camel casing, if we have like double C's. Okay, so when I was doing this kata, I discovered, so in my opinion, this is how it should be done, right? This is a camel case. It has to be a lower and then an upper. But actually, what the kata requires you to do on the website is to, in this case, for example, camel casing, I'll write it out here. Like camel casing, the solution should do, so it shouldn't separate just this, but it should separate this, this, and this, right? So basically it separates on every uppercase letter. I think that's not really what camel case is about, but anyway, that means we can just comment this is lower part out because it's not important. What's important is that it's followed by an uppercase character, right? And then if we reload this, then this will separate on every uppercase character, and this is actually the solution that passes on the website. But I think with this is actually for the description of the problem, it's more correct. Anyway, that's break camel case done. The last kata for this session is sort the odd. And this kata might seem a bit complicated. So the task is that you are given an array of numbers, of integers. You have to sort the odd numbers in ascending order while leaving the even numbers at their original positions. So an array of, or a list of 7 and 1, both odd numbers need to get sorted, so 1 and 7. Here we have a more general example that has even and odd numbers, so 5, 8, 6, 3, 4. 3 and 5 are odd, so we need to sort them. And so in the solution, 3 needs to come to the first place, 8 and 6, the even numbers stay the same, and then 5 is in the place of 3, and so on. So the way I think this problem can be solved is, first we can take all the odd numbers and sort them. Then we have a list of odd numbers sorted. And then what we can do is recursively go through our full list and for each element check that if it's an even element, we just leave it where it is and we move on. If it's an odd element, then we replace it from an element of our sorted list and process recursively the tail while dropping the odd element that we replaced it with from our odd list. Okay, so I will start with just defining the odds or odds. I'll just call it odds, but it's odd sorted. So this will be the list of odd numbers from our starting list. And so we can do this with filter. For example, we could use comprehensions, list comprehension, but we can do it with filter. So what we want to do is filter odd applied to XS, right? Except that we also want to sort it. So at the end, we want to sort it. So we can write it this way. So that's our odd list. And now what I want to do is like write a helper function that is going to do what I explained at the start. So I would call this function replace odds or sort odds. Sort odds. And the way I would apply this function is so to XS, but I would make this function to accept another argument, which is odds, right? The sorted list of odd numbers. And now I'm going to define this function. sort odds. I can write even the type signature. So it accepts a list of ints and another list of ints, and it gives back another list of ints. Okay, so sort odds. I'm gonna use pattern matching here. So we have two lists. If the first list is empty, the first list is our original list XS. So if our first list is empty, then we just return an empty list. But if our first list is empty, then the second one is going to be empty too. But in any case, we return the empty list. The second example is if the first list has some elements, but the second one is empty. So this would be the case where we have a list, but there are no odd elements, right? So the odds is empty, there are no odd elements. And in that case, we just return the even elements as they are, right? We don't care about sorting them. We just care about sorting the odd numbers. So those are the simple cases. And then sort odds of XS and YS, where both of them have some elements, will be, okay, so what will this be? Okay, I can write an if statement, right? I want to check that if okay, and instead of XS, I'm gonna write it as a pattern XS. So if X, the head of this current list of the initial list is even, okay, then I don't want to really do anything. I want to leave this element as it is. I want to say X and sorry, not solution, but sort odds. I want to just continue the recursion, right? I concatenate this X with the result of the recursion, and I call the recursion on XS and YS. Yes. Okay. And then else, if it is an odd element, then I don't want to put X as the odd element, but instead I want to put the head of YS, so the first element from my odds. So that will be the sorted element. So I want to put the head of YS concatenated with the recursively processed tail, right? Sort odds, and yeah, again XS. But now if I cannot just call it with YS, because if I call it with YS, then every odd element will be replaced with the first element of the odds list. So what I want to do is I want to recursively call it, but with tail S, right? So I take one element of the sorted list, and recursively in the recursive process, I drop that one element, and the next odd number will be replaced with the next sorted odd number. Okay, I think this is good. Sort is not in scope. We need to import data.list sort. Okay, I think this is good. So I will load this kata, sort the odd. Sort array is the function called, and let's check with this one. So 38654, that's good. And this one, oops, and this one 18365472990. Okay, that one is correct as well. So that's sort the odd done. It's maybe a bit complicated, but I hope I explained it okay. That's the end of this session. Thank you for watching and see you in the next one.